What is dark matter and what is dark energy? All right, so before we discuss dark matter, we need to talk about what's in the solar system. In the solar system, this is the relationship where this is the distance from the sun, and this is the orbital velocity. Why is the relationship like this? If the So let's just say that's the sun, this is Earth, and that's Pluto. Can you see that the period for Pluto is much longer than the period for Earth? Because number one, Pluto's orbit is longer than the Earth's orbit. So the period for Pluto is larger. For Earth, the period is shorter. So it's shorter for Earth, longer for Pluto. If you have the equation 2 pi r divided by t, and that's equal to v, that is one equation. Another equation is if you remember Newton's law of gravitation, so you equate the gravitational forces with centripetal force, and you rearrange for v. That is what you get. So when r increases, v will decrease. So this is the pattern for the solar system. For the planets, the further away the planet is from the sun, the orbital velocity decreases. So let's just say that again. The further away the planet is from the sun, the orbital velocity for those planets will decrease. Because it's further away, the period gets longer, and the orbital velocity will go down. Right, so that's what we observe for our solar system. Now let's talk about galaxies. Our galaxy, let's talk about a spiral galaxy. So this is a spiral galaxy. These dots represent stars or solar systems. So you've got stars and planets. So you've got solar system there, and a solar system there. Now, this is what we predict should happen. So this should resemble that. This region should be the same as this. This is predicted. However, that's not what we observe. What we observe is completely different. So we observe is that dotted line. The velocity of those stars on the outer edge of the galaxy is fast. So we observe the stars to be fast. So something is wrong, something is going on, something is missing. And we call that dark matter. It's all to do with assuming, you assume the center of mass is at the center. So because we're assuming that the center of mass is at the center, the prediction is like this. However, there is missing matter, and the center of mass must be somewhere else. And why do we get this? Well, we just do not know. So we call this dark matter. And what about dark energy? Let's talk about supernovae now. Now, supernovae type 1a, they emit a characteristic light. However, we observe this characteristic light to be less intense. Now, an explanation for this is that the expansion of the universe is increasing. So it's accelerating. Another evidence that the universe is expanding is, of course, the galaxies moving away. So it's redshift. We see that the wavelength is getting longer. So that is evidence for the expanding universe. All right, so the supernovae emits characteristic light. It is less intense when we observe it on Earth. One reason or one explanation for this is that the expanding universe is accelerating. Now, this is dark energy, because what is causing this acceleration? What is causing this expansion? At the moment, we don't know. We don't know what's causing the expansion. We call this dark energy because this permeates all of space. Now, dark energy accounts for 68%. So 68% of dark energy accounts for everything in the universe. If you look at this diagram here, the part where it is labeled C, it is being red shifted because it's moving away from us. So let's just say that you were looking in the middle, straight line from B, and you're looking at C. The arrow is going away from you, so therefore it is being red shifted and it's going towards the end part of the spectrum. If you're looking straight at B, the wavelength should be the same. And if you're looking at A, because it's coming towards you, it's being blue shifted. So the wavelength has gotten shorter, and at C, the wavelength has gotten longer. So there, it is being red shifted at C and blue shifted at A. For this graph, on the y-axis, you have the orbital speed. It's measured in kilometers per second. And on the x-axis, you have the mean distance from the sun measured in astronomical units. So if you remember the term astronomical unit, it is the mean distance from the Earth to the sun, and that is roughly 150 million kilometers. Right, so if you look at this graph, as the mean distance increases, the orbital speed decreases. And what is the reason for this? As the planet gets further away from the sun, the time for one orbit will increase. So therefore, the orbital speed decreases. For this graph, if you look at the y-axis, you have orbital speed on the y-axis, again, kilometers per second. And on the x-axis, you've got distance from the center of Milky Way, thousands of light years. Now, what is the difference between this graph and the previous graph? In the previous graph, you have a graph that looks like an inverse relationship. However, for this one, can you see that if it's less than 10 thousands of if it's less than 10 thousands of light years, it goes up, and then it goes horizontal, roughly horizontal. So it doesn't follow the model for the solar system, because in the solar system, as the planet increases in distance from the sun, the time it takes to orbit the sun increases, and that was an inverse relationship. For this graph, there is no inverse relationship, so something is not going on. They both do not match. If you look at this graph here, on the y-axis you have orbital velocity measured in kilometers per second, and on the x-axis you've got distance from center, thousands of light years. So for this graph you have 4 different galaxies, and if you can see, the graph increases at the beginning and then it goes almost horizontal as the distance increases. So there is no inverse relationship similar to the one in our solar system. The reason why this does not match is because we assume that the center of mass is in the center. Here it looks like the center of mass is nowhere near the center. So that is why it is probably horizontal. And we call this dark matter because we just don't know where that extra matter comes from. We can't see where it is. That is why these graphs confirm missing mass. For this graph, the dotted line A shows the predicted based on our solar system. So if you remember, if the planet increases, if the planet's distance from the sun increases, the orbital period will increase. That means the orbital speed or the orbital velocity will decrease. But that's not what we observe. We observe the line part B. So for B, we see that the orbital velocity remains almost constant. Now, if we assume that the center of mass is at the center, that is what we would get for A. For B, the center of mass is uniform. And what that means is that this dark matter is throughout the whole universe. It's throughout the whole galaxy, rather than our solar system. So that is why we call this dark matter.